Maintainability. It is well known that majority of the cost of software is not in its initial development, but in its ongoing maintenance, fixing bugs, keeping its systems operational, investigating failures, adapting it to new platforms, modifying it for new use cases, repaying technical debt, and adding new features. So, maintainability actually costs more than just creating a software because it needs to evolve as your product evolves and the environment and your customer evolves. Yet, unfortunately, many people working on a software systems dislike maintenance of so-called legacy systems. Perhaps it involves fixing other people's mistakes or working with platforms that are now outdated or systems that were forced to do things they were intended for. However, we can and should design software in such a way that it will hopefully minimize pain during maintenance and thus avoid creating legacy software ourselves. As previously, with reliability and scalability, there are no easy solutions for achieving these goals. Rather, we will try to think about systems with operability, simplicity, and evolvability in mind. To this end, we will pay particular attention to three design principles for software systems. Operability, make it easy for operation teams to keep the system running smoothly. Simplicity, make it easy for new engineers to understand the system by removing as much complexity as possible from the system. Note that this is not the same as simplicity of the user interface. Evolvability, make it easy for engineers to make changes to the system in the future, adapting it for unanticipated use cases as requirements change, also known as extensibility, modifiability, or plasticity. Operability, making life easy for operations. It has been suggested that good operations can often work around the limitations of bad or incomplete software, but good software cannot run reliably with bad operations. Operations teams are vital to keeping a software system running smoothly. A good operations team typically is responsible for the following and more: monitoring the health of the system and quickly restoring service if it goes into a bad state, tracking down the cause of problems such as system failures or degraded performance, keeping software and platforms up to date, including security patches, keeping tabs on different systems affect on how different systems affect each other so that a problematic change can be avoided before it causes damage, anticipating future problems and solving them before they occur, capacity planning, establishing good practices and tools for deployment, configuration management, and more. Performing complex maintenance tasks such as moving an application from one platform to another. Maintaining the security of the system as configuration changes are made. Defining processes that make operations predictable and help keep the production environment stable. Preserving the organization's knowledge about the system, even as individual people come and go. Good operability means making routine tasks easy, allowing the operations teams to focus their efforts on high value activities. So one of the key thing about maintainability is focusing on high value activity and automating those low value activity. Data systems can do various things to make routine tasks easy, including providing visibility into the runtime behavior and internals of the system with good monitoring, providing good support for automation and integration with standard tools, avoiding dependency on individual machines, allowing machines to be taken down for maintenance while the system as a whole continues running uninterrupted. providing good documentation and an easy to understand operational model. If I do X, Y will happen. Providing good default behavior, but also giving administrators the freedom to override defaults when needed. Self-healing where appropriate, but also giving administrators manual control over the system state when needed. Exhibiting predictable behavior, minimizing surprises. Simplicity, managing complexity. Small software projects can have delightfully simple and expressive code, but as projects get larger, they often become very complex and difficult to understand. This complexity slows down everyone who needs to work on the system, further increasing the cost of maintenance. A software project marred in complexity is sometimes described as a big ball of mud. So there's also a downside of complexity. You should only apply, I mean, in this case, you should only apply complexity when it really needed in the problem. So you also need to keep it simple. So you need to balance achieving for complexity just so you could provide advanced capabilities, but also you need to balance that with simplicity that will still allow your colleagues to maintain it. There are various possible symptoms of complexity: explosion of the state space, tight coupling of modules, tangled dependencies, inconsistent naming and terminology, etc. So, a consistent naming that aligns with your team and has a properties with almost describing what the function are doing, kind of like the least recently used or frequently used, most recently used are one of the name that you should strive for in your project, because it's easy, and also if you know or you understand all the design principles we discussed in the previous video, this would be easier. When complexity makes maintenance hard, budgets and schedule are often overrun. In complex software, there's also a great risk of introducing bugs when making a change. When the system is harder for developer to understand and reason about, hidden assumptions, unintended consequences, and unexpected interactions are more easily overlooked. Conversely, reducing complexity greatly improves the maintainability of software, and thus simplicity should be a key goal of the system we build. Making a system simpler does not necessarily mean reducing its functionality. It can also mean removing accidental complexity. Mostly in Marx, define complexity as accidental if it's not inherent in the problem that the software solves, as seen by the user, but arises only from implementation. So this accidental complexity term are highly connected to the implementation model we discussed in design videos. One of the best tools we have for removing accidental complexity is abstraction. A good abstraction can hide a great deal. So I just want to expand on this. We discussed abstraction in OS, and OS did a lot of abstraction to lessen the burden to the user space, and TCP also does that. So this layering actually are very important concept in computer science, even in writing codes. So a good abstraction can hide a great deal of implementation detail behind a clean, simple to understand user interface. A good abstraction can also be used for a wide range of different applications. Not only is this reuse more efficient than re-implementing a similar thing multiple times, but it also leads to higher quality software. As quality improves in the abstracted components, benefit all applications that use it. So if you improve those quality, for example, your front end, the other layer will also improve. For example, high level programming language are abstractions that hide machine code, CPU registers, and syscalls. SQL is an abstraction that hides complete on-disk and in-memory data structures, concurrent requests from other clients, and inconsistencies after crashes. Of course, when programming in a high-level language, we are still using machine code, we're just not using it directly, because the programming language abstraction saves us from having to think about it. However, finding a good abstraction is very hard. In the field of distributed systems, although there are many good algorithms, it is much less clear how we should be packaging them into abstractions that help us keep the complexity of the system at a manageable level. For example, we created a React application where one of the page for our video component or video room, including the panel, the collapsible panel behind it, are in one page. So it's less clear, or it's very hard to find abstraction or to actually decide whether we will separate the panels inside it, so that we could better read it, or we would change its directory or create a new component out of it. So it's very hard. You really need to think about it deeply. Throughout this book, we will keep our eyes open for good abstraction that allow us to extract parts of a large system into a well-defined, reusable components. Evolvability, making change easy. It's extremely unlikely that your system's requirements will remain unchanged forever. They are much more likely to be in constant flux. You learn new facts, previously unanticipated use cases emerge. Business priorities change, users request new features, new platform replace old platforms, legal or regulatory requirements change, growth of the system forces architectural changes, which meant you have to be prepared for large effort development, again, etc. So this is most often the difference between application that scale or that produce value over time versus those who were stuck and needs to go back with in the drawing board to redesign their system. You usually need to think about this at the start before you even start your project. In terms of organizational processes, agile working patterns provide a framework for adapting to change. The Agile community has also developed technical tools and patterns that are helpful when developing software in a frequently changing environment, such as test-driven development, TDD, and refactoring. Most discussions of these Agile techniques focus on a fairly small, local scale, a couple of source code files within the same application. In this book, we search for ways of increasing agility on the level of a larger data system, perhaps consisting of several different applications or services with different characteristics. For example, how would you refactor Twitter architecture for assembling home timelines, describing load on page 11 from approach 1 to approach 2? The ease with which you can modify a data system and adapt it to changing requirements is closely linked to its simplicity and its abstractions. Simple and easy to understand systems are usually easier to modify than complex ones. So that's the statistics for that. Probably, or usually, or mostly, the it's easier, for example, your code to be extended if you refactor that from 500 lines to 300 lines, and if it's in the different directory or in the separate component, it will be easier to refactor that. But since this is such an important idea, we will use a different word to refer to agility on a data system level, which we will call evolvability. Summary: in this chapter, we explored some fundamental ways of thinking about data-intensive applications. An application has to meet various requirements in order to be useful. These are functional requirements, what it should do, such as allowing data to be stored, retrieved, searched, and processed in various and some non-functional requirements. General properties like security, reliability, compliance, scalability, compatibility, and maintainability. So those are the non-functional requirements that you also need to achieve in your design, not just the functional requirements, which is what it should do, such as what database, what it will store in the database, whether it's document, data model, how would you retrieve it, how would you search that, and also a non-functional like evolvability, maintainability, reliability, and compliance are interconnected. You usually have to think about those uh, simultaneously in your mind while creating your app if you're a full stack developer. There's unfortunately no easy fix for making applications reliable, scalable, or maintainable. Unfortunately, there's no secret to making those trade-offs. You really have to understand your system and decide which fits with your system with relates to your goal. So a design knowledge or a research, being able to research and decide on the trade-offs is actually important. That's why the human interaction design and the data structure and algorithm is also an important subject or prerequisites before studying or creating this data intensive application. However, there are certain patterns and techniques that keep reappearing in different kinds of applications. In the next few chapters, we will take a look at some example of data systems and analyze how they work toward those goals. So it's really different for different use cases. So I think deciding based on that, if you take human to computer interaction seriously, you will be able to do that, those basics, and reading this available databases and how it works in understanding how it actually works with relates to OS in the real world will actually solidify your understanding of your application and how you can better extend its features moving forward. Data models and query languages. Data models are perhaps the most important part of developing software because they have such a profound effect on how the software is written. Most applications are built by layering one data model on top of another. For each layer, the quick question is, how is it represented in terms of the next lower layer, for example? So we talk about this in TCP or IP, but we also talk about this when it comes to database. Whenever we talk about our data models or our database, we also need to think about the query language or the structure of our app, whether our app actually have interconnected data, just like a Facebook. In that case, a graph data model is suited for that. For example, as an application developer, you look at the real world in which there are people, organization, goods, actions, money flows, sensors, etc., and model it in terms of objects or data structures and APIs that manipulate those data structures. Those structures are often specific to your application. When you want to store those data structures, you express them in terms of a general purpose data models such as JSON or XML documents, tables in a relational database, or a graph model. The engineers who built your database software decided on a way of representing that JSON or XML or relational or graph data in terms of bytes in memory on disk or on a network. So that's often the thing that is abstracted to software developers or working with the user space programs, is that talking with the hardware such as DMA or from hardware to disk or from Wi-Fi interference or from NIC, those are actually were created by embedded engineers. So they chose a way to abstract the representation of bytes to our software, to that lower layer software, which is the OS. So in terms of bytes in memory on disk or on a network, actually we will discuss the internals of database with different database in the real world and how they actually interact with our OS and with the memory in the future. The representation may allow the data to be queried, searched, manipulated, and processed in various ways. On yet lower levels, hardware engineers have figured out how to represent bytes in terms of electrical currents, pulses of light, magnetic fields, and more. In a complex application, there may be more intermediary levels, such as APIs built upon APIs, but the basic idea is still the same. Each layer hides the complexity of the layers below it by providing a clean data model. These abstractions allow different groups of people, for example, the engineers at the database vendor and the application developer using their database, to work together effectively. It can take a lot of efforts to master just one data model. Think how many books there are on relational data modeling. Building software is hard enough, even when working with just one data model, or even with working with user space layer when looking on TCP over IP layer view, or OS level, etc., and without worrying about its inner workings. But since the data model has such a profound effect on what software above it can and can't do, it's important to choose one that is appropriate to the application. There's also a design layer in which you look what is actually the most important functions that your user wants. So there's another layer. Working at that layer alone, not even on the front end and not even the back end, are actually hard enough. It could take an entire career or entire role to do just that. So it's important to choose one that is appropriate to the application. Relational model versus document model. The best known data model today is probably that of SQL, based on the relational model proposed by Edgar Codd in 1970. Data is organized into relations, called tables in SQL, where each relation is an ordered collection of tuples, rows in SQL. We will discuss this in the next video.